One is LinUCB applied to Monte Carlo tree search. Mandai. Yes.
I am Mandai from the University of Tokyo. Today I'm very glad to be here. I'd like to talk about my research about LinUCB applied to Monte Carlo research. As you know, the UCT has achieved remarkable success, and some UCT variants incorporate domain knowledge, such as for simulation improvement and for search ordering. In this study, we introduce another way for incorporating knowledge into MCTS by using the algorithm called LinUCB. This algorithm was motivated from the field of web article recommendation. This diagram illustrates the overview of this presentation. Multi-armed bandit programs, Monte Carlo tree research, and our proposals. And then I'll talk about our experiments on our artificial trees with feature vector. Firstly, I'll explain the LinUCB by comparing the UCB1. As you know, in UCB1 settings, we can observe the number of trials and the cumulative levers for each of arms. Then the choosing criterion consists of the empirical mean and bias star. On the other hand, in LinUCB setting, we can observe the feature vector of R, as well as the number of trials and cumulative levers. And the choosing criterion is calculated by the regression of the reward with the feature vector. In UCB1, if we want to evaluate the arm, we have to try the arm at least once. But in LinUCB, thanks to the regression, we can predict the evaluation by the arms that already have been tried before. Again, the LinUCB algorithm is for where we can observe the arm feature vectors. LinUCB assumes that the expectation of the lever is linear on its feature vector. Therefore, the expectation of a lever can be expressed by the inner product of a feature vector and an unknown coefficient vector. LinUCB estimates the coefficient vector through the trials by the linked regression. This slide explains the linked regression simply. Suppose we have tried arms n times, and therefore we have n training data. Each training data consists of a feature vector of an arm as an input and the reward as output. In linked regression, the objective function is this function. The function consists of a prediction error term and L2 penalty term. By solving this function with respect to theta hat, we obtain this closed form. Theta hat can be decomposed into matrix A and vector B. This matrix A plays an important role in the next slide. The regression has the property about the prediction error. The error is bounded by this square root term. LinUCB was formulated as the arm selection criterion by this property. This criterion means reasonable UCB1 type criterion. To sum them up, the LinUCB algorithm is made up by this procedure. The first part calculates the criterion of each arm, and then choose the arm with the greatest LinUCB value. And then the payoff of the arm is observed. In the bottom, the regression is updated by the reward of this time. Okay. By using LinUCB algorithm, we propose a new Monte Carlo tree search method. Hereafter, I will explain about our proposed algorithm. First, we propose a simple combination of LinUCB and LinCTS. As you might think, in the first version of LinUCT, we just use the LinUCB value instead of UCB1. And for LinUCB, we modified the update process. I'll explain the detail of LinUCT claim by comparing the UCT. In the selection phase, LinUCT claim chooses the node with the greatest LinUCB value instead of UCB1 value. Each child is considered as an arm with future vector instead of just an arm. Then, the selection phase continues until it reaches the leaf. In expansion phase, the both algorithms do the same procedure. And simulation too. It observes the reward of the simulation. In back propagation phase, LinUCB claim updates the regression matrix and the regression matrix and vector by LinUCB algorithm. The vectors are from the nodes that the algorithm has. Okay. This simple algorithm has a flaw. In LinUCT claim, the prediction criterion formula only contains this node vector. So in this tree at the node star, if the x1 is not similar to x1 prime, the prediction fails and it chooses the right side. So we need to avoid the prediction failure in this situation. So to avoid that, we also propose the variants of LinUCT. I'll explain the variants named LinUCT Lave and LinUCT FP. I'll explain the first one. LinUCT Lave is the combination of LinUCB value and UCB1 value. This formula is motivated from Lave formula, which consists of a rapid action term and the actual simulation result term. By this formula, the algorithm can evaluate nodes correctly in later phase. In early phases, it can predict the node value by LinUCB value. Therefore, in a sense, this framework can be seen as a generalized version of Lave. So this is the LinUCT Lave. Next, we also consider the other solution, namely LinUCT FP. As I mentioned, the problem is that we cannot reflect the p-value value to the upper node. So if we can replace the feature vector here by that of p-value, so we can evaluate the node correctly. Then we modify the propagation process to propagate the leaf feature vector to the parent node. In back propagation phase, we add the procedure that update the feature vector by its child feature vector. the propagation process continues until it reaches the root node. Why we thought this procedure was promising is because that if the PV is chosen more than others, so the feature vector x becomes x1 prime. So and multiple tree search might be the result. Then we perform experiments to see the performances of these algorithms. The experiments were performed on incremental random trees because we want to observe the domain-independent performances. To do so, we extend P-game. Here, I talk about P-game a little. In P-game, a tree is constructed. And then, the random variables are assigned to each edge. Then, the score of each leaf is calculated by summing the edge score from root node to the leaf node. Okay. Similarly, in our tree, a tree is constructed. Then, a random feature vector is assigned to the root node. Then, create feature vectors for each child node. Then, the feature vector is similar to that of the parent node. The property, this process imitates the process imitates the transition of the game state. Please refer our papers for a detailed process. And then the score of a leaf node is calculated by the inner product of each feature vector and trees fitting coefficient vector theta. The reward of each trial is the Bernoulli trial, and the probability that the Bernoulli trial will success is the leaf score. And then experiments were performed on our tree. For each experiment, an instance of our tree is created, and the best move is identified by the minimax tree search. Then an algorithm runs on an instance. Then we record the output node and observe the output is correct or not at each time. For each algorithm, we perform this procedure on 100 trees and obtain the failure rates of each time by averaging these results. The details are follows. Depth and branching factor are fixed, and we get rid of the instance that has two or more best moves. We also observe the regrets, but I'll show the failure rates on this slide. The compared algorithm were as follows: UCT for best case, and LinUCB plane for simple implementation, and modified algorithms, LinUCB late and LinUCB FB, and the combination with them, LinUCB late FB. Here, I refer them as LinUCB plus. First of all, we observed the parameter dependencies of our LinUCB algorithm. But the result was not interesting, so please see our paper for more details. Then we compared the performances of these algorithms. This figure shows the failure rates of each algorithm. The vertical means the failure rate because then the bottom is better. Then the horizontal means the number of players. the tree depth is 4, and the tree branching factor is 4. As you can see, the results of LinUCB and UCT are similar. For this size of tree, the difference is not critical. Then we also plotted the failure rate versus branching factor. This figure shows the failure rates of each algorithm at playouts 10,000, and the depth is 4.
You mean depth of the tree or which depth? What is depth?
Depth is 3. 3 depths.
Okay. And branching factor is branching factor of the tree.
Oh, sorry.
You say branching factor is 4.
Yeah.
That means the tree has branching factor 4.
Yes.
So your small trees only.
Yes.
Okay.
And then, as we expected, LinUCB plane performed worse than any other algorithm. Then we found that the performances of LinUCB Plus is superior to the UCT algorithm, especially when the branching factor is greater. Summarizing the experiments, LinUCB plane, the simple implementation performed worse, even though the tree settings are ideal for LinUCB, where the Olympiad was linear on its feature vector. And LinUCB Plus were better than UCT, particularly the tree was large. So we found that LinUCB could improve in CTS if we adapt it for the tree structure, where reward is linear. I conclude my presentation. We propose a new way to incorporate domain knowledge into MCTS. Also, we propose a simple incremental tree with feature vector. Then, through the experiments, we found that we need to adapt within UCB for trees for incorporating it to MCTS. That is the end of my presentation.
Question?
I have 2 questions. So, in doing the matrix inversion, I would imagine this would add a lot of, computational expense. In doing this, were all of these trials done without respect to how much time was taken to make the decisions? Do you have a sense of how it affects the runtime of the evaluation?
You mean that the LinUCB algorithm is slower than UCB, right?
Yeah, I'm trying to get a sense of that.
Yeah, pretty slow. So if we want to apply the LinUCB for layout games, we need to implement an efficient tree. So and the reason why the LinUCB is slow is that we need to compute the inverse of matrix. So
Yeah.
There. The Chrome matrix is n squared, n to the power of 3. So, but if we use diagonal matrix, the computational time is n. So, and we also check the performances of LinUCB, which uses a diagonal matrix. Then the performance is the first pair, not bad. So
My second question. First, I want to say that I'm very glad to see work being done to find alternatives to UCB1 because it relies on two assumptions that don't hold in our case. First, that the distribution is normal. Second, that the distribution is fixed. We expect these distributions to change as we find different lines of play. So I'm glad to see this sort of work, but one of the things that UCB1 does that's important is it tries to address in some way the exploration-exploitation trade-off. And that if you get a couple bad simulations along the line, that you have you will revisit it and to make sure that you don't put all of your effort into another line of play if you've just been unlucky in the first few trials. And so what I'm wondering is, are there features that you incorporate that somehow make this continue to balance exploration and exploitation, or are the features independent of, the ratio of selections to the total number of selections of the node?
Yeah, you were like, yes.
Well, this means yes, he is completely right.
Yeah.
So you do incorporate the ratio of selections of that arm to the total number of selections
yes.
as one of the features? I'm trying to understand how the right-hand side serves to give a boost to those arms that have not been selected as much as other arms.
Yeah, to my best knowledge, the original paper demonstrates that property.
Perhaps another way to get at this is, what are the features that you're using for this experimentation? What features are in the feature vector?
Our experiment. I'm sorry.
You're using random features.
Yes. Random.
Random features?
Yeah.
In a random tree.
Okay.
Do you have an idea of what you would use in a real program? What kind of features would you use?
Now time is time. So we have to investigate that which feature is effective or not.
This question, in fact, is how do we generalize your results to, I would say, particular games or particular set of features?
Such as for Go or for Hex?
I will observe the performances of LinUCB on Go, because Go is relatively large branching factors, and then I will observe the result.
Let me put it this way, you said the Go has a large number of branching factors, so we should do something with that. I have seen several methods, for instance, with the UCB in the Monte Carlo research, and I would like to tune UCB much more by, I would say, offering the following mechanism, and this is your mechanism. Sorry. This is a new mechanism for tuning the UCB.
New mechanism.
Yes, new methods.
Yes.
Yes. But I would say, Oscar put it already, with random features in a random tree, it works, yes. But what does it say for particular cases? We cannot say anything about it.
Yeah.
We only could express our hope. Yes.
Yeah.
Okay. So that is the answer to your question also.
I still, there are many things I don't understand, but
Okay.
we can move on.
Could you just make a commentary here? I think that the work that's been presented here is presenting a result in of itself. I don't think the speaker is pretending to have solutions to all our problems. I think as a result, it is of worth.
Yes.
And as to how it can be extended further, is probably even more complex than the result that the speaker has actually got. So it is a very deep thing.
Yes.
I think as a piece of information, our knowledge of what is going on has been pushed forward a little further, which is what I think the speaker intends to do, and I'm very glad that he has done.
I fully agree with you. I only would like to have this, I would say, shown even more on my, on a table to see as a mechanism we all can use for our, our own.
Which is ultimately why we are pushing the frontiers forward.
Yes.
And,
yes.
And hopefully draw that energy back on the problems that are ultimately significant.
Yes. Yes. Thank you.
Just a simple question. Do you think your idea can be applied to simple regret stuff? Simple regret.
Simple regret.
Maybe it is a future work, I'm not sure. Have you thought of linear stuff to simple regret?
Maybe